This is our first lecture video on Chapter 9, Chemical Bonding and Lewis Theory. So what I'd like for you to do is watch the YouTube video. So it's the ionic versus covalent bonding video. So it's on YouTube and you can just click on it and go to that link. So we want to review the three types of chemical bonding. And if you remember, the three types of chemical bonding are ionic, and then there's metallic, and then there's covalent. So we're going to review all of those three types of bonding. So I first want to focus on ionic bonding. So typically metals are combined with nonmetals. So typically metals are combined with nonmetals. So anytime you look at a formula and you see a metal and a nonmetal, there's going to be some ionic bonding in the situation. And in that case, the electrons are not shared. So they're not shared because we have ionic interactions. This is because there are cations and then there are anions. And remember, those cations are positively charged. You can think about that T in the center, it looks like a plus sign, and then the anions are negative. So here we have an example of sodium chloride. Notice how everything's all nice and neatly packed. Each one of those green spheres represents the chloride, and so they are packed very neatly in this face-centered cubic packing. And these sodium ions, the gray spheres, are in the octahedral holes of the sodium chloride. So to make the sodium chloride salt that contains these sodium cations and the chloride anions, the sodium metal, which is neutral, and that's going to have metallic bonding, it had to give up one of its electrons and transfer it to the neutral chlorine to make a chloride. So there we have a redox reaction occurring to make the sodium chloride. And here we have the ionic interactions. So you have the positive and negative attracting each other, and the negative and negative repulsions, and the positive and positive repulsions. So the next one that I want to look at is covalent bonding. And if you see nonmetals combine with nonmetals, you should think covalent bonding. So nonmetals combine with other nonmetals. And here the electrons are shared between two atoms. So covalent, so they're shared between the two atoms. Now there's electron density that links the two atoms together. So they link it or they bond the two atoms together. So in this case where we have chlorine and bromine coming together, each one of those has a valence electron that is unpaired, and when they come together they make a bond of at least two electrons. So these have two electrons in that bond, so it shares those two electrons in between them to make a covalent bond. And then with the metallic bonding, this is metals combined with metals. So here we have the representation of sodium, so sodium metal, and here we have each of those sodium ions, and notice that they're all nice and neatly packed, just like we had with the ionic material, but this time we don't have cations and anions in there. Instead, the valence electrons are free to transfer between the different atoms, so they can move about to the different metal atoms in nearby. So this creates what we call this electron sea. So the electrons are shared with all the other metal atoms, and there's no direct link between each metal atom. You've got this overlapping electron densities of these molecular orbitals, and it creates this sea of electron density, so the electrons can just move all throughout the metal, and that's why the metals conduct electricity. So we refer to this metallic bonding, we say there is a sea of electrons. So we're going to go back and start looking at Lewis dot symbols and how that relates to covalent compounds. And also gives an idea of how ionic compounds form when we transfer electrons. So when we're using Lewis dot symbols, we want to use the outer electrons. So use the outer electrons from the electron configuration. And we're using those electrons from the electron configuration to determine the number of electrons that surround an atom. And when we create the Lewis dot symbol for an atom, we want to spread out the electrons evenly about all four sides of the atomic symbol. So if we're looking at oxygen, remember that electron configuration is helium, 2s2, 2p4. Thus there are 6 electrons in that outer shell of oxygen. So we added up the 2 here and the 4 here. Notice that we can use the group number for a shortcut. Now, since there are 6 electrons around the oxygen, 1, 2, 3, 4, 5, 6. So notice that I've spread about my electrons equally around the oxygen atom. So here are how we would do the other elements, just using the group number. So the alkali metals only have 1 valence electrons. The alkaline earth have 2. The boron group has 3, and carbon 4, nitrogen 5. The oxygen group, also known as the chalcogens, have 6. The halogens have 7. And then the noble gases have a filled outer shell. So they have 8 electrons around them. So using what we know about the electron configuration of an atom, and we know that things want to fill their valence shell, so they want to have 8 electrons around them. So this is where we get the octet rule. Let's think about what would happen if we react lithium metal with fluorine gas. So we want to think about our trend. So we have lithium, which is a solid because it's a metal, and fluorine, remember that is one of our diatomic gases. So here we're reacting a metal and a non-metal. And if we think about the lithium, I'm going to just go down here at the bottom and draw my Lewis electron dot symbol. So the lithium has 1 valence electron, and the fluorine, so I'm just going to draw the fluorine atom, has 7 valence electrons. So to complete the octet, what about if we shared these 2 electrons, the one on the lithium and the one on the fluorine? But we can't share that because that would be a covalent bond, and this is a metal and a non-metal, so we can't do that. But rather than sharing, what about if we just said, hey lithium, let's get rid of your electron and just give it to the fluorine. So what we do is we make lithium plus and then fluorine minus, because we have the sharing of electron density. So if we go back to our reaction up here, we would expect to make lithium fluoride as an ionic solid. So we have the metallic lithium, we have the covalent, and we have the non-metal fluorine. So we have a metal and a non-metal coming together, so that's going to make an ionic solid. Now I need to balance my chemical equation because I have 2 fluorines here, so I need 2 fluorines on the other side. This now gives me 2 lithiums and 1 lithium over here, so I'm going to have to add a 2 in front here so that my equation is balanced. Now another way I could have approached this problem is using the electron configuration. Because remember, for lithium, the electron configuration is 1s2, then 2s1, and then that for the fluorine is 1s2, 2s2, 2p5. So lithium can give up that electron in the 2s, and then it has a noble gas configuration, because remember that 1s2 is the same thing as helium, so that would have a noble gas configuration. And then when the fluorine receives that electron from the lithium, it puts it into that 2p orbital. So then we have 8 valence electrons in the fluorine, and that becomes like neon. So we have the lithium plus, which is 1s2, and the fluorine minus, which is 1s2, 2s2, 2p6. And then if I want to show this using orbital diagrams, so the 1s and then the 2s, so we're looking at lithium here, and we'll put fluorine down here at the bottom, so that's 1s, 2s, and then there's 3 p orbitals, so that's the 2p. So lithium, we said, has 1s2, so 2 electrons in the 1s and 1 electron in the 2s. We said fluorine had 2 electrons in the 1s, 2 electrons in the 2s, and then 5 electrons in the 2p. So 1, 2, 3, 4, 5. So these are all 3 different ways of representing the same information. And of course, if I go ahead and finish out my analogy, so the lithium plus and the fluorine minus. So there's our 1s, 2s, and these are my 2p, my 1s here, and my 2s here. So I've still got the 2 electrons in the 2s. I gave away my 2s so they could go to the fluorine. And so our fluorine would have a full valence shell. So again, this is just 3 ways to convey the same information. But see how much easier it was to do it with the Lewis dot symbols, where we had the 1 electron for the lithium, the 7 for the fluorine, and we just gave that electron to the fluorine to make a fluoride. Okay, so let's go back and focus on ionic bonding and ionic solids. So ionic solids. These are 3-dimensional arrays of ions that are organized into regularly repeating patterns, and these arrays are called crystal lattices. Now, if we're looking at some of the properties of ionic solids, first of all, they conduct electricity in water and when melted. So they conduct electricity in water and when melted or molten. They are also brittle, which means if you hit them with a hammer or something like that, they'll crumble, they'll break apart. And they also have very high melting points. So ionic solids form crystal lattices because those lattices are the most stable. So if they're the most stable, energy is released when lattices form. Because remember, we start off at one energy level, and if it's going to be more stable, it's going to be lower in energy. So if we start off with an energy level here and we end up down here because it's more stable, you're lower down. That means that you had a change in energy that's negative, and so that negative is withdrawal out of our energy bank account, so that means the energy was released. Lattice energy. That's the energy of change accompanying the formation of 1 mole of ionic solids from a gas of ions. So we can write that as some gas A, some cation, and a gaseous anion coming together to form the ionic solid. Now, to better understand what happens in the formation of an ionic solid and figuring out the lattice energy, we sometimes use Bourne-Haber cycles. And Bourne-Haber cycles are very useful because they give us a visual image. They give us a visual image of the key enthalpy terms in the formation of a solid. And it also allows you to determine an unknown value if all the others are known. And when an ionic solid is formed, energy is always given off. So here we have kind of a generic picture of a Bourne-Haber cycle. At the very bottom, we start off with our ionic material, so our metal and our anion in the solid form and the ionic form. We then have to use the delta H of formation to break this up into the metal and the non-metal in their natural states. But going in this direction is the delta H of formation, but we're going to go in the opposite direction. So we want to break them up, so we want to decompose them rather than form them. So we're going to have to use the negative delta H of formation for going up. And each step as we go up the Bourne-Haber cycle, those are endothermic steps. So endothermic, because we have to put energy in for those reactions to occur. So if those are endothermic steps, the delta H values are positive. So we break everything up into its natural states in the elemental form. Then we have to get the metal and the non-metal in the gaseous form, so we may have to sublime it or melt it and then vaporize it, but we have to do something to get it from the metal and from its normal state to the gaseous state. And then once you've got it both in the gaseous state, then we have to ionize our metal so that we have the right charge of our metal. And then once we're at the top here, then we give that electron 2x, and hopefully you recognize that as the electron affinity reaction. And then this last part here, this last step, that value is the lattice energy. And so as you come down, those are all exothermic steps. So exothermic steps. And exothermic steps, because we're withdrawing energy out of our system, that's a negative sign. So those all have negative delta H values. So here we have a Bourne-Haber cycle for lithium fluoride. And they've given us some information. Now, if this information isn't given to you in the problem, you will have to look this information up. So we're going to start off with lithium fluoride here at the bottom. And we're going to use the delta H of formation for lithium fluoride. So that reaction is lithium solid plus half of equivalent of fluorine going to lithium fluoride. So let's just write that out really quick. So lithium solid plus 0.5 of F2 going to form lithium fluoride. So the delta H of formation for that reaction going in this direction is negative 617. But we need to go from the lithium fluoride into the elemental forms. So we have to use the positive value, so that's 617 kilojoules. Now our next step that I'm going to do is I'm going to break the fluorine atom, the fluorine molecule into the fluorine atom. So the bond energy for fluorine is 159 kilojoules per mole. So the bond energy that is the amount of energy it takes to break that fluorine bond. So fluorine going to 2 equivalents of fluorine. Now notice that in our reaction here that we only have half of equivalent of fluorine gas, the F2. So rather than using the 159, we have to divide that by 2. So we're only going to have to add 79.5 kilojoules per mole to break half a mole of the fluorine bonds. Now my next step, since I've got the fluorine gas, and that's where I need it to be, I'm going to start working with my metal. So I'm going to go from the solid to the gas, and that is going to be the delta H of atomization for lithium. So going from the solid to the gaseous phase, that's going to cost me 161 kilojoules of energy. Now my next step is to ionize my lithium. So I need to yank off an electron from lithium. So that's my ionization energy of lithium. So lithium going to lithium plus 1 electron. And that's going to require 520 kilojoules. And then my last reaction, I need to give that electron to my fluorine. So that's the electron affinity. So F plus 1 electron gives me my F minus, and that's going to cost me 328 kilojoules. So I'm going to have that amount released. So now I've got my lithium plus my cation in the gaseous form, my anion, my fluoride in the gaseous form. So now when these two come together, that value is minus 1050 kilojoules, and that represents my lattice energy. So if I were to add all of these steps and I complete my cycle, these would all add up to 0. So if I add 617 plus 79.5 plus 161 plus 520 plus negative 328 plus x equals 0, I can solve for x and I would get a value of negative 1050 kilojoules. So we see the cycle as we transition through. So this also gives us an idea. So this 520, we've got a larger vector here to show that this requires more energy for the ionization than it does to go from the lithium solid to the lithium gas. So we just have an idea of how much energy this takes by the size of these arrows. Now another way to look at this is using Hess's law. So we could add up all of these reactions to get our overall reaction of lithium and fluoride.